let me introduce a new concept called the directional derivative. And this is a concept that is intimately related to the gradient. So first of all, let me write the notation for this. So the directional derivative is often denoted as nabla with a subscript vector v of f, or sometimes it's written as capital D with subscript vector v of f, and sometimes, and this is my favorite notation, it's the partial derivative of a function f with respect to vector v. Okay, I like this notation because it is the most intuitive one. So how is it possible that you have a vector instead of the variable? Okay, so let's look at the definition. So the definition of this directional derivative is the following. The directional derivative of f with respect to vector v is equal to the limit when h goes to 0 of some fraction, which is the function f evaluated at r plus h times v minus the function f evaluated at r divided by h. Okay? So what's the meaning of this? Let's think about what each of these terms represents. So imagine we are using a function of x and y, so a two-dimensional case so that I can plot it. Okay? So we have some two-dimensional function. Let's draw x and y as a plane. So we have some position vector r, which goes from the origin to some position r. And then we can calculate f of r. That will be what's the value of this function at this position. Okay? Next we can evaluate, so that will be this. But now, what is this? The function of r plus h times v. Okay, so we can draw a direction v. And now we can scale this direction v by some number h, which is going to be very small. Okay, so let me zoom in and let me draw a vector which is h times v. So a very tiny version of v. Okay, so therefore we have this new vector pointing to this new location, which will be called r plus h times v. That will be the location vector r plus h times v. And now we evaluate the function at that point. Okay, so I will need some space. I'm going to move this v out of the way. So now if we evaluate the function at this point, that will be the function at r plus h times v. Okay, so I'm not going to try plotting. Normally we plot, as you know, in the z-axis we would plot f of xy, and this would be a surface, so that the height of the surface at these 2 points would be the function evaluated at those 2 points. But I'm not going to do that because it would obscure the diagram too much. But try to think of what this means. If we subtract f of r plus hv minus f of r, we are looking at the height above this point and subtracting it to the height above this point. So this difference in heights, so the difference in heights is on the numerator. Of course, if we make h smaller and smaller, that difference will be smaller and smaller. But then we divide by h, so this kind of compensates for the fact that we can make h very small. So this is telling us how fast is f changing in the direction of the vector v. Okay? And if you think about it, this is a generalization of partial derivatives. Why is that? Because remember, the definition of a partial derivative of f with respect to x was the limit when h goes to 0 of f of x plus h comma y minus f of xy divided by h. That was the definition of the partial derivative with respect to h. But this is exactly what you would obtain if you did the directional derivative of f with respect to the vector x hat. Okay, because if you use the vector x hat, now the limit when h goes to 0. So let me substitute all of this. Actually, let me copy and paste the definition of the directional derivative. And now wherever v appears, now I will substitute x hat. Okay, so I write x hat here. Okay, so now what is r plus h x hat? So this is equal to vector r is just xy plus h times x hat, which is 1, 0. So this is the vector x plus h y. Okay, so this becomes exactly this, x plus h comma y. Okay, so indeed you see that the partial derivative with respect to x can also be seen as the directional derivative of f in the direction x hat. Okay, so therefore you can think of the directional derivative as the partial derivative, but in any direction you want. Okay, so you could choose any unit vector. So you could choose df with respect to u hat, and that would tell you how fast is f changing in the direction. How fast is f changing in the direction u hat. Okay, so this seems like a very useful concept. And how do we calculate it? Turns out it's remarkably simple. We calculate it by using the gradient. So look at this. The directional derivative of f with respect to vector v is simply equal to the gradient of f dot product with v. And that's it. Beautiful. So this is the gradient of f, which is a vector field, and this is the direction of the derivative, of the directional derivative. Okay, so that's really neat. Also, there is a nice conclusion that we can take from this, and it is that the gradient of f necessarily is perpendicular to the contour lines. You remember this? You remember when we had a function of xy, a scalar function of xy, and we could draw it using the contours. So if this is a maximum, we could do contour lines. Yeah, and then the gradient, I said it's always perpendicular to these contour lines. So this can now be justified very easily, because if you calculate the directional derivative, so if we use as our vector v, we use a direction. If we use v, if we calculate the directional derivative with respect to v using v as the direction following the contour line, okay, so we use v following the contour line. If we are here and the contour line is here, we choose the direction tangent to the contour line. So by definition of contour line, by definition of the meaning of the contour line, yeah, the function does not change when we move along the contour line, and therefore the directional derivative of f with respect to v must be equal to 0, yeah, by definition of the meaning of the contour line. But we just saw that the directional derivative is the gradient of f multiplied by v. So the gradient of f dot product by v. So if this is 0, this must mean that the gradient of f is perpendicular to v. Okay, so this is a very nice, concise proof of why the gradient is always perpendicular to the contour lines. Okay, so I hope that's clear. Thank you very much for watching. See you in the next video.